All right, thank you very much. So first of all, I would like to thank the organizer for the invitation to speak today. And so this work will be based on my joint work with Yoonbok Lee and Xiannan Lee. And it started, when Yoonbok visited us in Manhattan, Kansas, not New York. And the name of Manhattan, Kansas actually was named originally kind of inspired by Manhattan, New York. So it's great that I get to present this work for the first time in this city. Okay, and similar to Adam, so I'm going to go to Oxford and give the same talk. So I apologize in advance if you're going to go there. All right, so I'm going to talk about some statistics of L function, but before we get to that, so let's look at the inspiration of this, which is Katz and Sarnak philosophy. So, they study an example of L function over function fields, and then they conjecture that statistics of nice family of L function should, in the large scale limit, match statistic in the large statistic for large random matrix from one of the classical compact groups. It can be unitary, orthogonal. Orthogonal can be split into even or odd, or symplectic groups there. And in this talk, we're going to consider some statistics related to low-lying zeros of L function. And we're going to kind of rephrase this conjecture into, well, we're going to look at the behavior of zero near s equal to 1/2. And that's a low-lying zeros. And in a nice family, that should coincide with the behavior of eigenvalues near one of matrix in one of the classical compact groups that I mentioned earlier. Okay, so I'll look at the first statistic, which is one-level density. Okay, so throughout the talk, I will assume the generalized Riemann hypothesis for L function. So if you're not familiar with it, so the famous example is the Riemann zeta function there. Okay, so since we assume GRH, the zero of L function can be written in the form of 1/2 plus I gamma f, and gamma f is a real number. And I'll let CF to be analytic conductor of this L function. For example, for zeta 1/2 plus IT, the conductor will be T. And so this is kind of measure the complexity of L function. And we consider phi to be the even Schwarz function. We like this because it's rapidly decay as x go to infinity. So we look at the density of function here. So that's the sum of or 0 of phi of gamma f log CF over 2 pi. So you might wonder why we have this scaling here. So this has come from the average spacing of zeros of the L function, which is 2 pi over log CF. So we want to put this scaling so that the one that actually contribute will be really close. When gamma f is really close to 0, that means the 0 is really close to 1/2. Okay, so if C is big, gamma f will be small to contribute to this whole sum. All right, and I will look at the family. So nice family kind of depend on what we look at, but we want all L function in that family to kind of behave similarly, and the conductor will be around the same size, which is Q. And so the one-level density of this family will be the average of this density function there. You sum all the f there and divide by the size of it. All right. So let's see what we have for this one-level density. So according to Katz and Sarnak's conjecture, they have that as a limit of Q go to infinity. This should be equal to integral of phi x times some function here. And this is a density that will depend only on the symmetry of the family. For example, if L function is associated with the unitary group, this W should be 1. And if it's associated with the orthogonal group, this will be 1 plus delta naught over 2. And delta naught is the direct distribution. Okay? Well, and what's the conjecture here? The limit should be true when the Fourier transform phi hat has no restriction on the support. But what do we know? Well, we actually know some results. There are several works on this. And but the support for phi hat is compactly support, and the support is not really large. Usually it's like -1, 1, -2, 2, for example. But before we get to see some of these examples, so let's take a look at why we have this limitation in the support of phi hat. So to compute this type of one-level density, the first step of this is to use the thing called explicit formula, which connects the information of zeros of L function with the coefficient at prime powers. And if you're familiar with the proof of the prime number theorem, that's one example how to use explicit formula information about, if you want to know information about prime, you can get it from the zero of the Riemann zeta function. But this one, you're going to go the other way. You want to understand the information of the zero of L function, we're going to try to understand the information about prime here, the sum over primes. And you have phi, and you do some Merlin inversion and stuff, and you get phi hat here. Okay? And that's the limitation of the support is come from how much we understand about this sum over prime here. All right. Now let's see what we have, for example. So as I mentioned, there are several work on that, but I just skipped only 2 in this talk. So the first family is a family of Dirichlet L function associated with Dirichlet character modulo Q. And you want Q to be prime number. And this is done by Hughes and Runix in 2002. And their support is phi hat is go to -2, 2. And next is associated with the orthogonal family. And we look at the family of L function associated with the capital newform of weight K at level Q. And we will compute one level density when K is fixed and Q go to infinity. And this is done the first time by Iwaniak, Low, and Sarnak. Actually, they are the first group of people who compute one level density. And they compute several examples in the paper, so I'll just pick one of them. And the support for this, they assume GRH go up to -2, 2 again, and Q is square free. So recently, there's a work by Czech, Devin, Fiorelli, Matomaki, and Sodergran. So they get the support, still this number less than 2. But it's go to 2 as K to infinity. But that work don't need to assume the generalized Riemann hypothesis. So basically, it's almost as good as assuming GRH in this case. All right. And so what are these two families have in common? First, you can see that the boundary that is, the support that is -2, 2. But another thing that you have in common is that the size of this family is around Q. And the analytic conductor of this L function is also around Q. And turn out that this is a natural boundary for the current method that we have and the understanding about the sum over prime that we have. All right. Well, and you might wonder, can we extend the support? Well, so I'll present maybe 2 ways to do it. So first, maybe you can try to add a reasonable hypothesis in that. And that hypothesis will involve, of course, the sum over prime. For example, this is orthogonal family. So in the work of Iwaniak, Low, Sarnak again, one of the examples they have has kind of natural boundary at -2, 2. And they add the hypothesis regarding the cancellation of exponential sum over prime. And the support can be extended past -2, 2 over there. But it's not easy to prove that hypothesis. Okay. And Iwaniak probably know more. What did it? Okay. And another way to do this is to enlarge the size of family. So instead of having the family of size Q, we're going to do something bigger than Q. And this, we hope that when we have a bigger size of family, we might be able to understand the longer sum over primes. All right. And the first family that we're going to look at, and this is connected to the unitary family. Again, we look at Dirichlet L function, and we look at primitive Dirichlet L function with modulo Q of around psi Q. So previously in the work of Hughes and Runick, they just have this sum over chi here. And this family, you add extra average here. And with this extra average, the psi go from Q to Q squared. But the analytic conductor for this L function is around Q. Okay, and this is done by Draper, Pratt, and Blasiville. And they can extend the support a little bit more than minus 2,2. And this is an unconditional result. All right. But you might ask, what should be a natural boundary for this family? And maybe you can guess it should be a double. But yeah, it's primitive character, yes. Yeah. Yes. Yes. So those what do you mean, the earlier result? Yes. Okay. Let's move on. Okay. And so next. Yeah. Well, okay. So next, so we have Fiorelli Miller. So they consider almost the same. They actually don't have primitive. So they actually do the whole sum over chi there. But even with that, they need additional hypothesis in there. So other than GRH, they do need to assume something they call the averaging hypothesis. This is on the variance of primes in residue class, and the support can go up to minus 4,4 in that case. So in this talk, we're going to look at another type of family. Okay? So we're going to go to the one that associated to holomorphic Hecke eigenclass form. So again, we look at the space of class form of fixed weight K and level Q. So if you are not familiar with that, you can, and you know more about Dirichlet character, you can, the analogy of that, this is kind of like the whole Dirichlet character modulo Q. And you look at the space, this is a subspace of that, and this is a new form consisting of Hecke has new form there. And new form is kind of analogy of that is a primitive Dirichlet character. Okay? And so again, this family is psi Q, conductor around Q. So go back to the work of Yoonbok and Sarnak. So they look at this one level density, they just have the sum over F here and the Q here. Q is square free. So what they can prove is that this is orthogonal family. They get this density here with the support of minus 2,2. We're going to add an extra average. So similar to the Dirichlet function case, you still have Q that we don't do anything with it. So we add extra Q there. Okay? And we add just this function psi here just to control the psi of Q. That Q will be around the psi big Q there. And NQ is just kind of normalize this one here. And we will work with harmonic average instead of just regular average because it's easier to apply Peterson formula later. And so, again, this family is still around psi Q square. And the conductor is Q. And with this, there's a recent work by my joint work with Sieg Barrios and Xiannan Lee. We can actually get the support up to minus 4,4, assuming only the generalized Riemann hypothesis. We do not need extra assumption here. And we get the one level density that we expect. Okay? And that's the largest support you can see in the literature with this. All right. So in this talk, we're going to consider the higher moments of this one level density, and we're going to do it with this same large family of L function, and you're going to see some interesting statistics in that. Okay. And before we get on to that, so maybe we want to ask, why do we care about this one level density? One level density has a nice application with the proportion of non-vanishing at s equal to 1/2. And the non-vanishing application, in some family has an important application. For example, for the family of elliptic curve, this is connected to the rank of elliptic curve there. And with the wider support of phi hat, we get a better proportion of the non-vanishing of L function. So why is that? Well, this is kind of due to uncertainty principle here. So we want to get information that really close to s to 1/2. You want phi to be like kind of really capture the information at 1/2. You want the support of phi to be small. And when the support of phi is small, naturally the support of phi hat should be large with that. All right, and there's a related question to that. Well, you look at L 1/2. How about derivative of that? What is the non-vanishing of that? So how often does L function vanish to high order at s equal to 1/2? And so this kind of related to moment in a way that let's look at one level density first. So if L vanish to high order here, so we should look at the one level density and imagine that phi is non-negative and phi 0 is 1. So you're going to get that this one is big. So if you have a lot of 0 appearing there, it's big, this quantity will be big. And if quantity is big, you take the moment, it will get even bigger. And once it gets bigger, this is actually more sensitive to high multiplicities of 0, so you actually can get more information about the higher order of non-vanishing. All right. And this is the motivation that we study higher moments, and now we're going to define the nth-centered moment with that. Okay? Yes? Yeah. Yes. Yes. And it's related to N-level density. So it's just this index can be the same, but N-level density it needs to be distinct. So it's basically like inclusion, exclusion. Yeah. All right, so let's just go back to, this is density function we defined. This is one level density. But if you look at one level density in terms of kind of statistics, this is the expected value of t. And so the n-center moment, so when we talk about the moment, we want to subtract the expected value and do the power of that. And phi here can be different. So if they are different, you write it in terms of the product of this factor. But if they are the same, they're just basically just the nth moment. Okay, and let's see what are the results on this. So there's some work on that. So first, again, go back to the family of Dirichlet function with fixed prime modulo Q. This is unitary family. Hughes and Runick, they compute moment of that. And if you look at this, if you are probabilitists, you probably like them. This is Gaussian distribution. Okay, and C2 is the variance, that's the second moment. And they can compute the moment when m up to 2 over alpha, and alpha is some support here. So if you want to get nth moment, phi hat need to be inside minus 2 over n to 2 over n. And all phi I now the same. So they just look at the case when phi I is the same. So you add all the support here, 2 over n time. So you get that the support go up to 2. And again, you still see that the support go up to minus 2, 2. This is not surprising. This is still the family of psi Q and conductor Q there. It's the same as the one level density thing. Okay, so let's take a look at next, the orthogonal family, the one that we already considered new form, weight K, level Q. So that's a work by Hughes and Miller, and this is improved by Cohen and the 15 others of them. They are Steve Miller's IEU student. They also obtained that as Q go to infinity, the n-center moment of this family also converge to the n-center moment of Gaussian distribution. Again, mean C1, the one level density variance is the second moment. Again, the support is still less than 2. And now, the natural question is, can you extend the support? And if you extend the support, do you still see Gaussian distribution? All right. And so we have one level density that you can extend the support to -44. So last year, the student, IU student of Miller, Shi, Gilman, Jaber, Miller, and Tom, so they look at my work with Sig and Xiannan, and they study the n-center moment of this family. So they look at F in here and extra average over Q here. And phi I now is compactly support between sigma I minus sigma I and sigma I. Okay. So let's see what they have. So they have some condition on sigma I. So it's a little bit complicated here. So they have that the sum of sigma j need to go up to 3/2. And then partition the set here. It needs to satisfy this condition and this condition. So with this restriction, they get that, okay, the limit is this. And again, I forgot to mention in the previous work, all the main terms come only from the diagonal terms. And we're going to talk about diagonal terms a little bit later. Okay, so now let's take a look at what happens if phi I or phi I are equal. Well, it's converged to the n-center moment. As you recognize, this is like a Gaussian distribution still here, this kind of factor here. But if you plug in all sigma I to be the same in this equation, or this equation, you get that the sum of sigma I is go up to 1. So, yes. Yeah, so yes. Yeah. The part of what, sorry?
Contribution of terms in this explicit form that comes from squares of prime.
Yes.
Do you consider them as diagonal?
They are subtracted as a part of the mean. Yeah, that actually, okay, sorry, that actually a diagonal, sorry, I go back on that. So let's say P1, so let's say you have two n velocity, P1 times P2 should look like P squared. That's the diagonal term. Yeah. And that comes from Peterson formula. Yes. Yeah. All right. Okay, so next, we'll go back to that. So if you plug in all sigma I to be the same, you solve that. This is go up to 1. And this is, if you go remember that previously, or the support is like 2. So this is actually a little bit worse, like narrower than what we expect. So to improve the result, this is actually the phenomena that they need to take a different test function. Okay. For example, when n equal to 2, they take the support of phi 1 to go up to minus 3/2 to 3/2, and support of phi 2 go up to minus 5/6 to 5/6. You can add them up, you get that it's greater than 2. So this is, they extend the support that way, that phi I need to be different. But morally, we expect that we want something to be kind of simpler than that. You want the support to just go up to 4, like that, and not more than this type of condition. And this is kind of analogous to the one-level density that you can get the support up to minus 4. And phi I can be, you are free to take phi I to be anything. It doesn't need to be different function. Okay? And this is the result that I'm going to present today, and that's a recent work that I have with Yoonbok and Xiannan. So we just have this condition only go up to 4. And limit of this Q go to infinity of Cn will be equal to this Rn here. So I will not express what Rn is for now, but I will tell you how to set up this Rn later. And this Rn actually can be computed from the random matrix side. So that's analogous for this, n-centered moment from the random matrix theory. And this is associated with the full orthogonal group. Okay. But what I will show you is the formula when phi I to be the same. And we will see. So turn out that when phi I equal to phi, we get that is phi I has the support go up to 4 over n. And you see Gaussian distribution, but not just that, you see extra term here. Okay, and this is non-zero term. And this is come from the random matrix side. And if you're interested what it looks like, I put it in the end of the slide. I can show you at the end. And what does it say here is that this moment do not exhibit Gaussian distribution when the support get larger than 2. And in previous work, this type of term do not appear before because the support is too small to see this. All right. It does not, yeah. Like minus 4 for one level density. You don't see off-diagonal term there. Yeah, you see it when it go higher than one level density. Yeah. Yeah. And this one, you actually see the first time off-diagonal main term. And I will talk a little bit like what they look like. All right, so now, because there are new terms, so there are new challenges in this work that kind of contrary to the previous work. So first, we need to identify these off-diagonal main terms. So where are they? Okay, so this is actually the cause that you have a symmetric setup in the previous work of Schick and et al. And we have this thing that is look like a big term here. We call it oversized phantom contribution. This is from the thing called continuous spectrum. So I'll talk about this term later. But once we identify this term, we see that this term that you think is big, it disappears. And you can shift the contour further, and you actually get off-diagonal main terms that way. And this issue does not present in the one-level density case, n equal to 1. So we never see this before when we do at one-level density. All right. And the next thing that one-level density do not have is the combinatorial problem. So we face the problem of we have number theory results that look messy and random matrix results that look messy, but they don't look the same. So we don't know how to match them. Okay? So previously, Hughes and Miller, and in the previous work, Cohen et al., they used the method called cumulants to compute the n-centered moment from the random matrix side. And it's great, but then when support actually get larger, the off-diagonal main term contribute, the terms in both random matrix side and number theory side gets more complicated. And it's harder to solve the matching problem. So instead, we will refine Mason's network to resolve the matching problem. Okay. So I get to know this work like more than 10 years ago. I attend MRC workshop, so Conry taught me about this, and Mason is also my roommate, so I was aware of her work back then, and I did not expect that I'm going to use her work, more than 10 years later. All right. So let's look at random matrix size first. So Mason and Snett obtained a new formula for the n-level density for even orthogonal and symplectic groups in the random matrix size. And previously, this n-level density and correlation from random matrix size, they state in a nice form is determinant of certain matrix. It looks nice, but it's not easy to match with number theory result, because when you have number theoretic result, they don't look like determinant of the matrix. Okay, so, but they present new formula. You're gonna see the new formula in the next couple slides. And this formula actually gave an alternate and simpler way to match random matrix size with number theoretic result. For example, in the work of Rubinstein and Gauss, that they would compute a level density for the L function associated with quadratic Dirichlet character modulo around site Q. And this is associated with symplectic group. And their work is actually based on the work of Conry and Snett to calculate n correlation of the zero of the Riemann zeta function, which is connected to unitary groups. So basically, they express things in terms of the contour of the ratio of the characteristic polynomial. Okay. All right, so now we're going to define n-center moment for this orthogonal group. And this is what we set up to calculate. So let's O to be orthogonal matrix. And in orthogonal group, they can be separated into two parts. The first part is called even orthogonal. This is the part that determinant equal to 1. And the other part, we call it odd orthogonal. And this part has determinant -1. So the orthogonal group determinant can be plus or -1. And the full orthogonal group is the union of even and odd. Okay? And so if e to the I zeta is the eigenvalue of orthogonal matrix, we have that e to the minus I zeta also eigenvalue. This can be an exercise in a linear algebra class. And so for even orthogonal, you can write the eigenvalue as e plus and minus I zeta 1 to e plus and minus I zeta n. For the odd orthogonal, we have one extra term, which is plus and minus 1 here as an eigenvalue. So we can add them as plus and minus e to the I zeta 0 here. Okay, and now we look just at, since it's symmetry plus and minus, we can just look at the index from zeta 0 to zeta n, and it goes from 0 to pi instead of minus pi to pi. And then again, we will recall that the expected value for this one level density is this, and you do computation, it's phi hat plus phi x over 2. And so the n-center moment for full orthogonal group will kind of be defined separately. We have R even first, that integral over the even orthogonal, and the index will start from 1 to n. And we have the scaling of n over pi because this is average spacing of eigenvalue in the interval of pi, and there are n of them. So it's n over pi there. And then you subtract the expected value here. Similarly, for the odd orthogonal group, the index start from 0 here, so it's j equal to 0. Okay? And so we integrate over the measure induced by the Haar measure here. So what is the n-center moment for orthogonal group? You do even plus odd divided by 2. All right, so Mason and Snett work have something that almost what we want. So they actually have an expression for these two things, t plus and t minus. T plus is over even orthogonal, and the index look like this. So if you go back to look at the R even, is almost the same, except this term. Okay? So we just do inclusion, exclusion. So this is a linear combination of t plus n here, this term. Okay? So for odd orthogonal, it turned out that it has something really like the same as symplectic group here, except symplectic group has index that starts just from 1. They don't have j equal to 0 term. But the odd orthogonal has j equal to 0 term there. So when we remove the j equal to 0 term, we're going to have that R odd is basically the linear combination of the symplectic group. So we work with this combination there. All right. And so this is a big integral that we see. So this is Mason and Snett work. So they actually have the expression of t plus and minus of limit of some of them and the big control integral. I know it's a big formula, and I usually don't like to present big formula. You can basically ignore them. But I just want to see that it looks complicated. And to be honest, the first time I saw this, I'm actually not sure if it's going to work out. But I try to compute anyway. And it's actually nicer than I expect. Okay, this one looks big and scary. However, it has one advantage that you're going to see, a couple of advantages you're going to see. The first one is that even though it looks complicated, it expresses the answer in terms of test function where the Fourier transform is supported in any range. This is not something that happened before when the formula is in terms of determinant. Okay? So you go back there, and the whole thing here, what I want you to focus is W prime only. That actually the one that related to the support of the this phi here, and it appear here and here. Okay. Okay. All right. So basically, if the size of the W prime is large, then the support of large compared to the support of the Fourier transform, then the term will disappear. Okay? So the term that survives when W prime is small. So for example, when the support is less than 1, the case that only survives is when W prime equal to 0. And this turned out to be correspond to the diagonal terms from number theory side. And in the similar, kind of idea is that if the support go up to 2, the one that survive will be the size of W prime equal to 0 and W prime equal to 1 that contribute. So basically, this number that contribute should be less than the support here. Okay? If it's 1, you have 0. If it's 2, you have 0 and 1. And our support go up to 4. So since our support go up to 4, we have 0, 1, 2, 3 that contribute. Okay, so that's all you need to know about that formula. Okay. And so do we do some computation with that? It turned out that something nice happened after all this computation. R even will look like AI here. And therefore, term that survive 0, 1, 2, and 3 from W prime equal to 0, 1, 2, 3. R odd will look the same as R even, except this factor minus 1 to the I. So if you want the full Rn here, this is what we want. This is for orthogonal group. You add them up divided by 2. So you have A0 survive and A2 survive. We already see that A0 is diagonal term, so A2 will correspond to the off-diagonal term from the number theory side. And turn out that even though the formula looks scary, when you actually compute the contour, you see that the calculation of contour in random matrix side and the computation in the contour for the number theory side do mirror each other. You're going to see some similar computation there. And the way we pick up the pole and residue are also similar on both sides with this big formula. Okay. And you're going to see a little bit more of this analogy in the next 3-4 slides later. All right, so That's all for random matrix size. So we're going to move on to number theory size. So first of all, are there any questions before I move on? All right. I'll go to number theory side now. So for number theory side, so recall that this is what we want to compute. You have F here, sum over F, sum over Q, and the product of n term here. All right. And as I mentioned earlier, to compute this one level density, we connect the sum over 0 to the sum over prime. We do the same thing for n-center moment. We change the sum over 0 in this into the sum over prime. And the prime power basically don't contribute into the main term. So we just look at the sum over prime only. So it will look like that. So log P and lambda FPI is the coefficient in the L function of this family. All right. So what are we going to do? Well, we're going to multiply them out. You have lambda FPI here, and you're going to apply the thing called Peterson formula. You have sum over F to compute this. Okay? So in reality, we need the Peterson formula for the new form. And this is done by the work of Ng and Petro. And this is more complicated than the usual Peterson formula. You can kind of analogy of it like you have the sum over primitive character, for example, in Dirichlet L function. And you kind of need to do inclusion, exclusion, compared to the sum over all characters. Sum over all characters is easier. So this is the same way as that the new form will look more complicated. But to illustrate the idea in this talk, we're just going to do just the usual Peterson formula. And this is the usual one. So you sum over all form in the space here, and you have delta M equal to N. And this is what I mentioned earlier. This is diagonal term. Okay? And the rest is off-diagonal term. And the off-diagonal term will look like this. S, this is Krusterman sum. If you're not familiar with this, this is the definition of this. And this is J Bessel function. All right. Not familiar with that, just kind of take it for granted as a black box there. Right. And now let's look at the diagonal term. You want to create something that have M equal to N. All right, so as Henrik mentioned earlier, you're going to have something square. So this is what we have. You multiply lambda fp1 to lambda fpn out. You want to create square here where Ri are all distinct prime because you can put them into two parts, m and n. They are the same. So you have this term come out. Okay. And this term turned out to be matched with the A0 from random matrix side. Okay, so next is off-diagonal terms. Turn out that the off-diagonal term has interesting matching, okay, between number theory and random matrix as well. But the product of P1 to Pn need to look like this. First, you're going to have all distinct primes, R1 to R kappa, and this R kappa plus 1 to RL square. You can have this or don't have it. It doesn't matter. So this can be not one or have something there. But kappa here, I want it to be at least 2. Okay? So interesting part is that you go back to the big formula that I showed earlier. You have 3 parts here. W prime, you know that the off-diagonal term should come from when W prime equal to 0. And you have W double prime here. W prime union with W double prime should be at least 2. So this prime R1 to R kappa do corresponding to this set W prime union with W double prime. And this W1 to WR, they each have side 2. And you see something that has side 2 here, which is square. So R kappa 1 to RL square corresponding to each of W to WR. And you have this computation here. This is the one that gives you something look like Gaussian distribution. And it corresponds to this square of the prime. All right. So this is kind of what random matrix formula kind of show how to kind of match it more straightforward than, ugly formula look better. It's actually friendlier than a nice formula in this case. All right. Okay, so now we are down to just compute. I will just care only when R1 and R kappa. This one is not hard to deal with. So it will be the product of distinct primes in this case. All right, so now we want to apply Peterson formula to understand this type of sum here. So it's AM times lambda Fm over square root m. Am is coefficient, m is the product of distinct primes. The restriction of m, again, is go up to q to the 4 minus delta here. And this is come from the condition of phi hat here, that this is less than 4. And so we use Peterson formula, the off-diagonal term. We don't have the diagonal term there now. Will look like basically like this. So you have Kruszelman sum, J Bessel function. Okay. So you have sum over C and sum over Q. That's a good thing to have two sum. You can choose. You can sum C first and then sum Q. Or you can sum Q first and then sum C. And if you don't have this term, C and Q are kind of symmetry here. So you have choice. And what choice you're going to pick kind of depend on the size of Q and C. Whatever is bigger, you sum that first, and then you sum the small sum later. And because this is something that we're going to apply the thing called Kuznetsov formula, you want the level to be as small as we can because it's easier to bound the error term that way. Okay, so for simplicity, so we're going to analyze the size of C and Q. For simplicity, this J-Bessel function, what is nice is that we can just analyze it at the thing called transition region. This is when the size here is around size 1. So square root m over CQ is around size 1 in this case. So root m over CQ is 1. So C is around root m over Q. So remember that m go up to Q to the 4 minus delta. So the one that when we plug in here, we can see that C is Q to the minus 1 delta over 2. So which one is bigger between Q and C is actually Q. So you want to do the sum over Q first and then sum over C. So what is C in this case? So we call it complementary level C. So if you're familiar with the work on asymptotic last sieve of Conry, Xiannan, and Zhao, they have kind of analogous for that for Dirichlet function. They call it complementary trick there. So that's the conductor. So we do the level here instead. And now we're going to apply Kuznetsov formula to the sum over Q. And we do sum over C later. Okay? Again, this sum will look like this. Yes? Okay, let me think.
You can just limit your code work for holomorphic.
Okay.
On the other hand, you still need Kuznetsov formula for spectral completeness. Because you are switching C and Q, and Q has no favorite weight like Bessel functions in it.
Yeah.
So you need all the test functions. And for all the test functions, holomorphic are not complete in space.
Oh, okay. All right. Thanks. Thanks for the comment. Yes. Okay. So Yes, so we apply Kuznetsov here. And so what we have is, we have three types of sum. So we have the thing called holomorphic spectrum, discrete spectrum, and continuous spectrum. So the first two will be an error term. The last one, continuous spectrum, associated with Eisenstein series. This is the one that will give you off-diagonal main term. And so this is where we assume GRH. We need it because when we compute this error term here, so you have something like a product of this type of sum, and it's small when we assume GRH. And so this is coefficient that connected to the holomorphic form or mass form. The story of continuous spectrum is more interesting. So you need to, because you want to compute the off-diagonal main term explicitly, you do need an explicit coefficient for this, and we use the work of Blomer and Katz on it. So for Eisenstein series, it will look like a product of this following term here. So chi p log p, p to the 1/2 plus and minus it. So chi non-principal, again, you expect that this is small. Okay? And the main term will come from when chi is principal. And if you just look at this sum alone, it's actually generally large. The size is basically by prime number theorem, so you don't have chi p now. You just have log p over p to 1/2 plus and minus it. You have something like p to the 1/2 minus it. So this is large. Because p go up to q to the 4 minus delta, you get something greater than 1. You don't like it. Okay? This is larger than the main term, and this is the oversight contribution there. Now I'm going to talk about why it's not a problem in one-level density. In one-level density, you just have p to the it, and you actually have extra t average over there. And that is spectral parameter, so you have integration here. And p to it do oscillate. So once you oscillate, you have integration. You expect there's a lot of cancellation, so this is small. Okay? But the story is different when you go higher than one-level density. So for example, you look at n equal to 2. You have the product of two sums, right? So instead of p to the 1/2 minus it alone, you also have this p to 1/2 plus it. You pair them up, you get p1 over p2. So what happens when p1 is around the size of p2? This disappears. And when this disappears, you integral over t. It doesn't matter. It gives you a big term. You don't have anything oscillate for you to integral there. And so you put it in, this is actually large. And this is how this Sheik et al., they try to avoid this problem by, well, I'm just going to set up P1 to be greater than P2. So you have P1 over P2 still there. And you can integrate and make it small. But in our case, we don't want to do that. All right. But before we get on how to kind of fix that, so this is not the first time this oversight contribution come in the Eisenstein series. So this appear in the work, for example, Duke, Freelander, Iwaniez, and also Blomer, Humphrey, Kahn, and Milinovich. They start on the average over mass form in Eisenstein series. They do a Kuznetsov formula. They get another Eisenstein series. And then turn out that both are big, but they cancel each other. So what we have here is we're going to start with holomorphic modular form, and we're going to use orthogonality of the space of homomorphic Katz form instead. So what I say is, well, what we have is, so if we don't have this looks basically like a Peterson formula backward. We basically, if you just do the Kuznetsov, you just have no Eisenstein contribution. But what we have in more explicit calculation, this is from the Eisenstein series, this is from holomorphic. They are orthogonal to each other. So the integral is 0, they disappear. And so, but we have phi q, so we do Merlin transform there, and this is contribution of Eisenstein spectrum is non-zero. But we do have extra sum over C, so we do extra sum over C. And turn out that it roughly looks like this. So what I want to point out is that we have zeta 1 minus s and zeta 2 minus s here. And you might think that suppose at s equal to 0 because you have zeta 1. But what happens when s equal to 0? This is 0. You have this integral and it disappears. So you do not have the 0 as a pole there. So you can shift past the 0 and go to something that's close to 1. And that is where the diagonal main term is for off-diagonal main term. Okay. Yes. For Katz form, we yeah, so we bound them like by assuming GRH. So this is, you mean in the mass form case? Yeah, so that's a small. Okay, but this is part of this that we kind of make it kind of small from the beginning. So we think it's something we can, okay, maybe we can talk after the talk and in more detail about that. But I think that's all I want to talk. But thank you very much. Yeah.